Hello, Precalc. It is a nice, quiet Friday morning. Mrs. Contreras and I have our coffee. I think. Do you have coffee?
I do have coffee.
Excellent. And we are getting ourselves into symmetry and some reciprocal functions. How's your morning going?
I'm sleepy. These online days are so much more tiring than real life school.
Yeah, I think that's important to just say out loud. Like, this is hard. I think that's okay, but um, I think it's important to just not accept, but acknowledge. Jinx. I think we said that at the same time. Hopefully, on the recording
I
it
don't
did.
think we did, but it's okay.
All right, here we go. Go ahead and get started. Enough banter. We were talking about symmetry and reciprocal functions. We'll get to reciprocals later, to reciprocate. But we have here two definitions: even functions and odd functions. Now, these terms, even functions and odd functions, we have two definitions for both. One, two. One, two. And the first one for both of these definitions is a good definition, but the second one I think is more important. Mrs. Contreras, can you read to us the even function definitions?
So the even functions are functions that are symmetrical to the y-axis, but they're also defined as an even function's f of negative x equals f of x.
Awesome. So the only reason why I'm saying these two definitions are different is because later on, and I've said this before, if we're not graphing x versus y, if we're graphing in another coordinate system, some other coordinate systems include parametric or polar. Journal entry if you guys want to check out what those are. But if we're not graphing in the normal Cartesian coordinate plane, then that definition may not hold. However, the second definition, if in even functions, f of negative x is equal to f of x, that is what we mean when we say something's even. Can you read this, not in math notation, but kind of out loud, what it means?
Like interpret into regular human speak. I think when you're plugging in a value and the negative of that value, you're going to get out the same thing.
So like if I plug in like -2, I get 4. And if I plug in 2, I also get 4. And if we begin to do this for every value, we start to see that in the Cartesian coordinate plane, we do have this symmetry over the y-axis, the line x equals 0. If I plug in -1, if this function is even, this parabola, then when I plug in the opposite value, I should get the same value.
And I like how you're pointing out, Mr. Kirk, that x equals 0 is kind of like this border between the two sides, because 0 is between our positive and our negative numbers. So that's a nice way of thinking about it.
So in recap, even functions, when you plug in the opposite value, you should be getting the same value. All right, and when we're dealing with the Cartesian plane, we have symmetry across the y-axis. The odd function over here, want to go ahead and talk to us about this?
Functions that are symmetrical to the origin are a 180-degree rotation. And an odd function's f of negative x equals negative f of x.
So once again, this definition here at the top is useful when we're in the Cartesian coordinate plane, which we are. What do we mean by symmetric to the origin, 180-degree rotation?
So if you think about things that have like a rotational symmetry, that means that when you turn it around, and in this case, we're turning it around 180 degrees, then that is going to be the same. So for example, like the cube function, yeah, right there, x cubed. So when we take this part, that's in the in quadrant 1, and then we rotate it 180 degrees, we get what's in quadrant 3.
And similarly, when we take that thing in quadrant 3 and we rotate it 180 degrees, we get what's in quadrant 1. Right, so it's going to land right on top of each other. But as I said before, this is the actual definition that we care about. Right? It's all about inputs and outputs. Can you turn that into human speak?
When we plug in a value, we get out we get out something. And then when we plug in the negative of that value, we get out the negative of that something.
So like when I plug in 2, I get, it looks like 8. And what an odd function says, so when I plug in the opposite of that value, I get the opposite. When I plug in -2, I get -8. Right, and that's going to give us that rotational symmetry. Right? Even and odd functions. Let's just talk it out. What are some other examples of even and odd functions besides, of course, x squared for even and x cubed for odd?
Well, x to the 4th, x to the 6th, x to the 8th.
Ooh, so can I write this?
Even functions.
Oh, actually, let me.
And
such that 2n. How do you feel about this? 2n. Ooh, wait. How can I write what you were saying in a better way than what I'm doing?
We could say x to the 2n such that n is an integer.
Ooh, I like that. And we want it to be an integer. Cool. Is x to the 0 even?
X to 0 is just 1. And so that is even, yes, because that no matter what you plug in, you're going to get out 1, positives or negatives.
So we got x to the 2n. How about the absolute value of x?
Yeah, I think so. Yeah, because that takes away our negatives.
Mm-hmm.
Would it be x to the 2n plus k? Because we can also have like vertical translations.
Oh, yeah. I'm going to make that a whole new one just because I don't have room there. But x to the 2n plus k. And let's just carry this n throughout everything we write. And it's just going to be an integer wherever we write it. Yeah, because we can shift it up and down. A vertical shift doesn't affect if a function's even or not. I wonder how that'll play a role in the odd function.
It doesn't affect, a vertical shift doesn't affect if it's even, but I think it might change if it's odd or not.
I think so too, right? Because if I move this thing up, then I will be getting like 9 and -7. I will not be getting opposites. So absolutely. Now you couldn't see my mouse, but you'd get 9 and -7. It wouldn't be even. Sorry, it wouldn't be odd. And I got one more that I can think of, and I'm sure there's more, but let's not forget about our good old half circle function. That's even, right?
Yeah, that's even.
Yeah. Maybe we'll put right here a question. What other even functions can you think of? Maybe have a multiple choice of some options. How about some more odd functions?
Well, if we have 2 to the x to the 2n plus 1, as long as our exponent is some odd number, I think that's odd, but we can't do that vertical shift like you were saying. Like that's not something that works with, yeah, 0.
Yeah, plus we cannot have a vertical shift. Can we have a horizontal shift on any of these?
No, I don't think so, because then we would be shifting what our inputs would be, right?
Yeah, I think that's going to break both of these, both even and odd, right?
Mm-hmm. Mm-hmm.
What other odd functions do we have? Well, we have the x to the 2n plus. Oh, wait, no, that's what you just said. Sorry. What I meant, in my brain, what I was trying to say was that function. Is that function odd?
Yeah, I think so. Yeah.
Right. I wonder what happens when it's negative, though.
Oh, because then we would get some things that are undefined.
So we do need to be careful there.
We do need to be careful. I wonder if that's alluding to something in the future.
Ooh, and how about this one?
Is that odd? So if we plug in negative x, then we'll get out -1 over x, which is exactly our definition of odd. So I think, yeah, that works.
I think this is secretly the same as this one too, though, right?
Oh, because what if n was -1?
We'd be there, yeah.
Boom.
All right, so boom. Cool, but I think it also works over here.
We could do like a piecewise thing with our circle function. Right, we could take like this part and that part of 2 semicircles, and that would be odd. And it would still be a function.
So like we could get real fancy here. Boom, boom, boom. negative the square root of 25 minus x squared from negative 5 to 5.
Include,
And let's include this one. Uh-oh.
including negative 5, but go to 0.
Oh, that's what I meant. We go to 0.
But
And
then,
then I think
but then 0 would break things unless we don't include 0 in
let's
either
just
of
not
the
yeah, let's
intervals.
just not include 0.
0 just doesn't count.
Yeah. 0 messes things up very often in math. You're waking me up here. I'm getting excited. Cool. All right, so we got some odd functions here. We got some even functions here. We're understanding what even and odd is. Let's go ahead and verify whether a given function is even or odd. Go ahead and scroll on down. Hopefully the people that don't thrive off our energy in a normal video are having a great time right now, relaxing, and not being we're not being as obnoxious as we usually are.
I don't know. I'm getting really hyped. Like, this is exciting.
I know. So we are here. We have two functions here. We have f of x and g of x. I want to verify whether or not these are even or odd.
Well, our second definition for both even and odd was if you plugged in negative x, then we see what we get from there. Do you think that's a valid first step, Mr. Kirk?
I think so, because like we could plug in a value and get out a value and then think it's even or odd. But we would then need to verify that for every single value on the domain. And very often there's going to be an infinite number on the domain. So instead of verifying for one value, let's verify for all values. Let's do exactly what you've just said. Plug in negative x. As we're kind of composing functions here. We're taking the negative x function and putting it into the f function. So what's that going to look like?
3 over parentheses negative x, and that quantity squared plus 4.
Cool.
But when we square anything, we just get out the positive, right? So we have x squared plus 4 in our denominator. Oh, that's lovely. Well done, Mr. Kirk.
Just adding that little, like, I don't know, aside. And then we got 3 over x squared plus 4. And what is that?
I think that looks like our original f of x. So which one is that? Is that even or odd?
So f of negative x is equal to f of x. When we plug in the opposite value, we get the same value. That's going to be even, right? Yeah, we're plugging in. We're going to be symmetric across the y-axis, the line x equals 0.
I like the even dance. Like
you should like look into the void though.
When it's like tutting.
All right, this is the TikTok dance, right?
No? I'm not on TikTok. No? Sorry.
All right, so even. This one's even. Let's do the same thing for this next one. Maybe we'll get odd. Maybe. Yeah.
It looks kind of odd, right? Like all the exponents are odd, and then we have like an odd number.
Mm-hmm.
So yeah, let's try it. So g of negative x, that's 2 times negative x cubed plus negative x minus 9.
Okay. Do a little bit of cleaning up. Negative x cubed.
Negative x cubed.
Negative parentheses x cubed. Right, because negative times negative times negative is a negative. So that negative is just going to pop out. Plus negative x minus 9 minus 9. Is that f of x?
No, or g of x, I don't think so, because we have minus 2x cubed minus x minus 9. So all the signs changed where there were x's, but that minus 9 stayed the same. So yeah, if we factor out, then we're getting out a completely different function.
A very close to the original, but not the original. All right, so it's definitely not, this is not f of x.
G of x.
I keep saying that, and I correct it in my mind, but thank you for correcting me. This is not g of x. So it's not odd. It's not negative g of x. I'm feeling like this is neither.
But how can we like make sure?
Right? Because like, what if I made a mistake?
Yeah. What if we just plugged in like a number?
Oh, like a counterexample.
Yes, a counterexample.
Yeah, that's like a really powerful way to disprove things in mathematics. mathematics. Just find one example where it doesn't work and then you're done. I don't know, what value do you want to plug in? What looks easy to plug in?
Sorry, there's sirens outside. I live down the street from like a fire department.
Well, that's a good thing.
Yeah, I mean, yeah, it's not too bad. They actually do come around a lot. You should be concerned, maybe. So let's plug in. I don't know. It's early in the morning. Can we try 1?
Let's try 1 and -1. If it's even, we're gonna get the same thing. If it's odd, we're gonna get opposites. If it's neither, then we might get the same thing or opposites. We might need to check another thing. But if we get the fact that they're not the same at all, then we know it's neither. So 1 cubed is 1, times 2 is 2, plus 1 is 3, minus 9 is -6. And then -1 cubed is -1, times 2 is -2, minus 1 is -3, minus 9 is -12.
Those are super different numbers.
Counter example.
I like how you did the Mr. Culver's joke of counting on your fingers.
But it's like not a joke. It's like true. You can count on your fingers. Counter example used. This is neither. Let's make sure that we actually answer the question. Hopefully I spelled neither wrong. I before E, except after E, C, or when sounding like way, like in.
What? This is longer than the one that I know. I would just copy what's in the prompt.
Oh, yeah, there it is. It's in the prompt. Sweet. All right, let's proceed. So just to recap, if we want to verify if a function is even or odd, Mrs. Contreras, what do we do?
Well, first we plug in -x and see what we get. But then so if we get out our original function, that's even. If we get out the negative or the opposite of our original function, then it's odd. But if we don't get out either of those, then we should just plug in some numbers, like opposite numbers, and see what we get out. Because if those are very different, if they're not the magnitudes of each other, or if they're not equal, then we know that our function is neither even nor odd.
Well said, well summed up. Let's proceed. You ever watch the show Whose Line Is It Anyways?
Only like
20 years ago.
I feel like it was like a very long time ago.
True. I just like the sound effects game, and I thought, no one's gonna get what we're talking about. Maybe one person will. That's why we do it, for that one person that watches Whose Line Is It Anyway on YouTube. All right. So completely leaving the even and odd realm. Two topics today. This is in some ways similar to even and odd, but let's leave that in the past. Let's talk about reciprocal functions. Reciprocal, to reciprocate. I had a friend in middle school who every year for Halloween, he would go as the reciprocator. And it's almost Halloween, so it's kind of topical. But he would go as the reciprocator. And what he would do is he would go up to people, up to his friends, not to random people. And he would take whatever they're doing and grab it and then reciprocate it. It was it's such a middle schooler thing to do. He was the reciprocator.
That sounds like really obnoxious.
It was.
Not something we should support.
He's the band director now at SSI. So maybe some of our students know who this is, Mr. Wambach. But yes, the reciprocator. If you guys know Mr. Wambach, give him a hard time for me, please. To reciprocate, to flip, to flip upside down. So what are we gonna do here? What is the reciprocal of this line?
I think that maybe we should plug in some points, because it's early and my brain is still waking up. So the reciprocal of like one of the points, like 1, 1, right? The reciprocal of 1 is 1, so we got a point there.
Mm-hmm. And so the reciprocal of 1 is 1. Boom. Right, we're taking the outputs and we're flipping them upside down. What's the reciprocal of 2?
1/2. I can do that. That was an easy one.
What's the reciprocal of 1/2?
2.
Dang it, you got it. How about -1?
Oh, the reciprocal of -1. I need more coffee.
What about -1/2?
-2.
All right, let's, and I'm gonna get that the 1/2 as well, the -1/2. We'll speed up a little bit. How about what happens when it gets closer and closer to 0?
So like if we plug in like the closest number to 0 that I can think of in the positive direction, which is 1/10. Whoa.
That's gonna be 10, right?
That is
And same down
10.
here, negative 1/10. What if I plug in like -1 billionth?
Then you would go off the graph and you would get a billion or -1 billion.
-1 billion. All right, so we're getting bigger and bigger and bigger as we get closer and closer to 0. As you reciprocate graphs close to 0, what is the conclusion that we can make?
I think we're getting a vertical asymptote.
All right, so let me write these steps down. When you reciprocated 1, it was 1. Reciprocal of 1 is 1. And similarly, the reciprocal of -1 is -1, right? But when you reciprocate 0, we're going to get undefined, and we're going to put an asymptote there. So reciprocal of 0 is undefined. I don't want to say is an asymptote. That wouldn't make any sense. Undefined. But because of that, we put a asymptote.
An asymptote? Are we being fancy?
An asymptote, yes. And then what happens as I get smaller and smaller and smaller?
So smaller and smaller.
Well, actually, the reciprocal function. What happens when the function?
Right. So our function at like 10, right? We have 10, and then the reciprocal of 10 is 1/10. So
and then when it gets to
we're
a million,
getting smaller and smaller numbers.
So we're getting closer and closer to the horizontal line y equals 0. In this case, did we just graph 1/x?
I think we did, which we established earlier was an odd function. So if we do our rotational symmetry, I think it is. Yeah, that's odd.
All right. So this agrees with what we know 1/x to be. If we reciprocate x, we get 1/x. But I mean, if I said, hey, graph the reciprocal of x, you might have known to just graph 1/x. But what if the examples are a little bit more complicated? Like you don't know what they look like. What do we do?
Whoa. Well, in the first quadrant, we know what that's going to be because it's the exact same thing as what we had up top.
So it's going to be 1, and then it's going to be 1/2, 1/3, 1/4, 2, 10. Okay.
And then with our transformations, we talked about like what happens when you take absolute values of things, right? Because this is an absolute value function, so we're taking the absolute value of x. So we're gonna have the reciprocal. But if we think back to what we had up at the top, where we had I don't know how to do it. It's like this.
I'm adding that branch of that graphic up there. That's what we had before.
When we're taking that's what we had before, and so when we're taking the absolute value of that, then we're just gonna make all of the outputs positive.
Boom. So -1 becomes 1, -1/2 becomes -2 becomes 2. Similarly, -1/2 becomes 1/2, and we get this thing.
Whoa.
I call this the volcano function.
Oh.
Everything needs a silly name. This is the volcano.
You want to call it like the tree trunk function or something?
I guess you could call it a tree trunk function. I like volcano. Volcanoes are fun. I mean, trees are fun too, but there you go. We got one of our
like super fun. They're like kind of dangerous.
Yeah, but that's what makes them fun. All right. All right. So with this one, we want to take the reciprocal, and I think something interesting is going to happen. I know something interesting is going to happen. Take me to this one.
Yeah, because I think it looks like, well, so the reciprocal of the 0.01, that's pretty easy, right? That's just 1 again. But then everything else, it might be kind of wonky.
Okay.
Check, we got number 1. So it looks like this is a 2 to the x function.
So
Is that
let's just
right?
write that
Because we
down.
plug in 1. When we plug in 1, we get 2. So that is supporting our hypothesis. And if we plug in 2, we get 4, and that's also good. Plug in 3, and we get 8.
Okay.
So as we're growing like that, all of the values as we're going to the right from our our y-intercept, those are all going to be numbers bigger than 1. So when we reciprocate those, take the reciprocal, wait, grammar, then we get like 1/2 and then 1/4 and 1/8, and those numbers are going to get smaller and smaller and smaller as we're increasing what our x values are.
And that never gets.
What happens when it never gets to 0? Why?
It never gets to 0 because when as this number gets larger and larger and larger, we have the reciprocal of 1 over that large number, and 1 over nothing is going to give me 0. 1 over 1,000 is going to be 1/1000th. 1 over 1 million. If I go 1 million to the right, 1 over 1 million, that's still not 0. We have an asymptote here, right?
Asymptote.
Okay.
Oh, interesting. Because it looks very similar to the asymptote that we had for our original function on that other side. Interesting.
So what's this 1/2 going to do? 2?
Yeah.
And then I'm not really sure what these are, but we have this hypothesis. Let's like figure out what the function is. What is the reciprocal function?
The reciprocal function of 2 to the x?
1 over 2 to the x, right?
Yeah. Well, wait, isn't that one of our exponent property things?
So 1 over, let me do this. 1 over 2 to the x, is that fair?
Right? Because 1 to the x power is always going to be 1. So we can just factor that out.
Okay. I feel like there's a lot of things we can talk about here. What were you thinking? How do you want to rewrite 1 over 2 to the x?
Well, we could think of it as 1 over 2 to the x would give us like the negative exponent, right? So we have 2 to the negative x.
2 to the negative x. And these are the same, right? 1/2 to the x and 2 to the negative x?
Yeah.
Because 1/2 is 2 to the negative 1. Let's like work our way to what you jumped to right away. That's 2 to the negative 1 to the x. And then we get to what you claimed, 2 to the x, 2 to the negative x, sorry. Okay. What?
Because of power to a power, right?
Yeah. The power of a power is multiplication. Wait, but 2 to the negative x and 2 to the x, what transformation is that?
Oh, that's a reflection, isn't it?
We're taking f of x and not equals, but we are plugging in negative x. That's a reflection over the line y equals, the line x equals 0. The reciprocal of 2 to the x is a reflection over the line x equals 0.
Yeah. Wow.
Well, that is something beautiful about exponents. The reciprocal is not itself, but a reflection. That didn't happen in any of the problems we've done so far. Interesting. I wonder if this would work with 3 to the x or 4 to the x or 5 to the x. We'll leave that for, I guess, the viewer. Let's do some more. We're reciprocating functions. Use the given graph.
And we're going to try to sketch. We're trying to sketch g of x is 1 over f of x when we have this graph. So we have a parabola, and it's nice that this parabola is shifted off of the origin. Why is that really nice?
Well, if it was on the origin, wouldn't we have an asymptote?
Oh, yeah.
Right. So since it's been shifted up, we're going to have a reciprocal at every point. We'll never be undefined. 2 becomes 1/2. Let me zoom in a little bit. I think this one deserves to be zoomed in because that's going to be the highest point, I believe. Oh, let's go like 300%. Oh,
Wow, 300.
and so 2 became 1/2. Well, that's a 3. Let's put that at 1/3. It's a 3. Let's put that at 1/3. And then what's going to happen as I increase with x and decrease with x?
We're going to get similar to the 2 to the negative x power when we're going to the like off to the positive numbers. We're getting an asymptote. Something froze. Oh, it's okay.
I think it's just Zoom. And I've kind of crossed the x-axis right here. That was a mistake. Sorry about that. Boom. Okay, there we go. We got a reciprocal. It's as simple as that. Just take each of your points and then reciprocate them. And then there's patterns that we can notice. As it goes off to infinity, the reciprocal is going to go off to 0. This graph gets a name, Mrs. Contreras. Do you know what this graph's name is?
Oh, I don't know if I can pronounce it right, but it's like the Witch of Agnesi.
I think it's the
It's
second
named
one you
after
said. But we should,
Agnesi?
yeah.
It's named after Maria Agnesi. Now I can't say it like a normal human.
Right.
But I think some people have actually written about her in their journals. But if you have not yet, that is there's an idea for you right there.
Yeah. This is and it's a family of functions. There's lots of functions that look like this. It's when you reciprocate the parabola, and you get this graph that is defined everywhere. We don't have the volcano or the tree graph. We have it is defined everywhere. Let's move on over here. There's a lot going on in this one.
Whoa.
All right, so let's just use the tools that we've established at this point. Where am I going to have asymptotes? Vertical asymptotes.
Whenever we're hitting the x-axis.
So right here, right?
Mm-hmm.
Okay. And right here?
Between -4 and -3, yeah. This is where the little hash marks, the crosshairs, are really nice.
Oh, when you draw the line and then you turn it into... Yeah, maybe I should do that. Let me just do that for the sake of doing it.
Okay, can we do dashed lines though?
I thought we could. Maybe we can't. Maybe I'm wrong.
Oh.
And then right here, right?
Right there, yeah, at the bottom of our semicircle function.
Sweet. All right, cool. What are some other convenient points to just graph while we're at it?
Well, there's all the places where we're hitting one of the crosshairs. And you just take those fractions, right? So we have L at 0, 2, that becomes 0, 1/2.
0, 2 becomes 1/2.
-1, 5 becomes -1/5.
Do you mind if I add something?
Oh.
I like to... Oh, did I do it wrong?
No. I said it wrong. You
Okay.
did it right.
Can I add something? I like to just find out where it's -1 and where it's 1 and put points there.
Oh.
Because those points, when you reciprocate 1, you get 1. When you reciprocate -1, you get -1. All right. Am I going to continue down like an asymptote like this?
Well, no, because we can't take the reciprocal of something that's not defined, right? And
There's
our
nothing
function
there.
isn't defined between 9, 10. There's nothing there.
What's going to happen as I approach this, the asymptote at x equals 5 or x equals 4?
Well, we're dividing by really, really small numbers. So the reciprocal of small numbers is a big number. So we're going up to infinity and beyond, or not beyond.
I guess I'm kind of crazy by going from right to left. Maybe not.
I think this is really this is speaking to the left-handed people in our classes.
True. Are you left-handed?
No, I am not. Although for a while I did have an injury on my right hand, so then I had to like learn how to write with my left a little bit.
Well, I've made a mistake.
Difficult.
I'm going up to infinity, but then when I come back, I'm on the other side. The reciprocal of negative whatever is going to be super negative. So I like to
negative.
I like to call these teleporters. It like goes up to infinity and then teleports down. Comes back. I guess there's teleporting happening over here too. Then I think
a lot of teleport. Anytime I think we have not like continuous It's there's teleporting. Oh, did I spoil something?
I don't think so.
Okay.
Boom. I believe that's the graph right there. And I'm very unhappy with the fact that it doesn't go just as high. There we go. Cool. Not perfect, but it's a sketch. I'm happy with it. Yeah. It's okay to it's okay to not be a perfectionist in this scenario. So we need to scroll down a little bit here. We got one last one for you. When a function is undefined, what do we do about the reciprocal of a function that has an undefined part of its domain?
Well, can we do like the rest of it before we deal with that part?
Yeah, easily enough. So I see like a 1/2 there. So I'm gonna put a 2 there.
Nice. Well, we like the ones, right? So reciprocal of 1 is 1. And then reciprocal of -1, boom, there it is.
Okay.
Cool.
See something happening here? Let's keep going.
Well, there's like a 2, so we can do, yeah, -2, -1/2, +2 is a +1/2.
We got, yeah, +2, +1/2 right there. I saw this -1/4, so I put a -1/4.
Oh, nice, nice.
This is starting to come together.
It looks.
And that's like a 2/3, so let's put like a 3/2.
Oh yeah, there you go. This looks pretty liney to me.
Linear.
Yeah, linear.
Yeah, and you know what I can do? You know what I can do? I can boom, bada bing, bada boom.
Ooh,
Line cool. Boom. Alrighty. So this kind of looks like a line.
That does look like a line. Wait, but we have this vertical asymptote where our function is undefined, and I think we were talking about earlier that when we take the reciprocal of something that's undefined, what do we get?
1/f of -5. So it looks like we're getting 0, but that would mean that 1/undefined is equal to 0. Oh, question mark above this equal sign.
But that seems fishy.
I feel like when something's undefined, it's garbage. I'm trying to draw a garbage can.
It's just trash.
It's trash. And let me try to draw.
Can you do that in Oscar the Grouch colors?
I was gonna do that. I should have done it in Oscar, but I was gonna try to draw Oscar.
Oh, but now it's like a.
That's not a bad little stick figure, Oscar. This is trash. This is trash. Yeah. Something is undefined. The reciprocal of it is also undefined. So, what do you think we should do to address this?
We should just avoid it entirely, because that's what we can do with some problems. We can just avoid them. And why don't we put an open circle right there?
Let's put an open circle there. Yeah, it's a line. We've established that, but there's a hole whenever we have undefined graphs. What kind of graph does the let's call it like the pre-image graph, the one with the undefined domain? What do you think that parent function is?
I think that it's a line with the slope of.
What I'm saying is the original thing. What do you think that function is, or its parent function? Let me make it in red. What do you think the parent function of this thing is?
Oh, 1/x.
That was my bad. I was not phrasing my question very well. Yeah, that's a 1/x graph. So like, if f of x is some transformation on 1/x, then wouldn't it make sense that the final answer looks like a line?
Yeah, because when we were looking at the reciprocal of a line, we were getting the parent function 1/x.
I'm going to add right there, x cannot be 0. Because that's one of the things that we look for. We look for those inconsistencies. 1/x. If I do this like really slowly, 1/f of x is 1/1/x. X cannot be 0. There's a lot of ways to think about this. Yeah. Excellent. X. Oh, you did excellent. I was doing the Mr. Burns from The Simpsons. Excellent.
He creeps me out. He's weird.
When I was a little kid, I used to walk around like this. I had a camp counselor that made fun of me. She's like, "You look like Mr. Burns."
It's like a T-Rex kind of thing. Like,
So, when we are doing reciprocal functions, Mrs. Contreras, what do we need to kind of look out for? What are some tips, some tricks of the trade?
Some tips we like to look for where, because the reciprocal of 1 is 1 and the reciprocal of -1 is -1. So we like to pull those points out because we just have them. And then we need to look at when our function is going to be undefined, and we should just avoid the problem and put some open circles there.
Mm-hmm. And then this one doesn't address it, but what happens when our original function is 0?
Then we're getting a 1/0, which is not something that we can do. So we have vertical asymptotes there. And also when we have n behavior of our function going to infinity or negative infinity, then the reciprocal of infinity or negative infinity, that gets us a horizontal asymptote. It gets us closer and closer to 0.
Oh. So I got one last comment I guess I'll make before we close this one out. And that is, let me go ahead and add a page, just so everyone knows that that's a possibility as well. You can always add a blank page. But we've graphed all these parent functions. And we've now talked about how to graph reciprocal functions. So I guess one of the things that we can do now is, with few exceptions, graph or get a sketch of any function that is given to you. If I give you something ridiculous like, ooh, my calibration was off. Ooh, the calibration's very off. Let me try to write this with terrible calibration.
This is one of those teacher skills that no one tells you you pretty much always pick up.
Here's a function, f of x equals 2 over x squared plus 1. What would you do maybe if you want to graph that, maybe in your head, or get a sketch?
I would think about what parent function that kind of looks like, or what the parent function of the reciprocal looks like. And then I would use those tools, like we talked about, where finding things that are 1s, and then finding when things are undefined, and thinking about the end behaviors, and also keeping in mind what's allowed in my domain, and maybe what my range would also be. Wow, there's a lot of things to think about.
Right. But I think that everyone has the ability to graph that without using a graphing utility like Desmos or your graphing calculator, your TI. Because what goes on in my head there is what you're saying. I have x squared. I go up 1. I reciprocate, which becomes that Witch of Agnesi graph. And then I dilate by 2. So I know what this thing looks like kind of in my head. It's going to be, let me scroll up. It's going to look something like the graph I have here on the left. So we are slowly building all these tools so we can have a very holistic view at math in general, I think. If someone gives you a function, you know what it looks like. Or you can get yourself to the point where you know what it looks like with a few tools that you now have in your pocket. But I think that we are getting closer and closer to becoming graphing experts. I don't know.
Nice.
Yeah.
It's very like Captain America poses too.
I'm not sure if I'll be. Let me talk real quick so that my video gets highlighted. All right. So how do you want to close this one out?
Maybe what's the best thing you ate this week?
What's the best thing I ate this week? Can you go first while I think for a second?
Oh yeah, the best thing I ate was earlier today. I had food from Desi Market, which is like off of University. It's like next to Nick's Diner. Very good.
Man, I had a lot of good food this week. Man, last night there's a place in College Park called Marathon Deli.
Ooh, Marathon Deli.
And it just opened back up.
Nice.
And I swung by there, got some takeout. So that was delicious. I got a Euro. It was really good. All right. Ready to close this one out?
Yep.
Do you think that they noticed that our shirts changed?